Assalamu alaikum, everyone. Good evening. So, I'm going to be your lecturer today. My name is Enis Doko. I am from Turkey, Istanbul. I have PhD in physics, but I do mostly my research on science and religion and philosophy. And I'm associate professor of philosophy at Ibn Khaldun University at Istanbul. So today we are going to talk about the relation of Big Bang theory with atheism and the debate about the existence of God. So basically my talk or lecture will be composed of three parts. First, I will introduce the science, that is, I will introduce the Big Bang theory. Then in the second part, I will discuss the implications of how Big Bang theory supports the arguments for the existence of God. And then in the third part, I will take your questions, inshallah. So let's start with the first part, the scientific part, the Big Bang theory. The story of Big Bang theory can be started in 1920s. So if you look at the night sky, we see stars. Well, actually, each star is similar to our sun. Our sun is an example of star. And in the 1920s, people thought that actually all these stars form the Milky Way galaxy, and Milky Way galaxy is the entire universe. Of course, there was a debate, some questioned this, but we thought that all universe is made up of single galaxy. Then in 1920s, early 1920s, Edwin Hubble was able to disprove this claim. Basically, he was able to prove that actually our closest galaxy, Andromeda, is separate from the Milky Way galaxy. Then he continued to observe further different galaxies and discover them. Basically, Hubble also could deduce the distance of the stars from the Earth by comparing their luminosity, that's their energy, and brightness. Brightness of light decreases proportionally with the distance, actually with the inverse of the distance. So by measuring the luminosity and brightness, you can calculate how far away the galaxies are. So basically, not only he was discovering new galaxies, but Hubble was also measuring their distances from the Earth. And Hubble, when he was discovering these galaxies and mapping their distances, he actually observed that as we move away from Earth, that's from Milky Way galaxy, the galaxies are moving away from us with an increasing velocity proportional to the distance. Basically, it's easy to see how he made this discovery. If we take a light source, suppose I have a light source at my hand, it's white. If I move away from you very fast, of course, you will see that the light at my hand shifts to red. This is called redshift. If I move towards you, it will shift to blue or bluish colors. So basically what Hubble was able to observe was that the more distant a galaxy is from us, its light is shifting more towards red color, which means the galaxies, the further away they are from us, they are moving much faster away from us. He was able to put these discovered galaxies, as you can see, into a graph. And as you move away in terms of the distance, as you can see in the graph, actually their velocity increases. They are moving away from us faster and faster. This is called the Hubble's law. So what's the meaning of the Hubble's law or discovery? Of course, this was an experimental discovery. Actually, in 1915, Einstein developed the general theory of relativity. It's a scientific theory which explains the behavior of the gravity and space-time, basically, how gravity and energy influences the space-time. If you solve the general theory of relativity's equations for the whole universe, assuming that universe is roughly almost homogeneously distributed, you discover that either the universe must be collapsing to itself or expanding. Einstein was unhappy from this result because if you look at the night sky, if you look at the stars, they don't seem to be moving away or coming towards us, which means it seems universe is neither expanding nor collapsing. As such, Einstein tried to fix his equations so that they don't imply universe which is expanding. So actually, before Hubble was able to observe that distant galaxies are moving away, Einstein predicted by his equations, his famous general theory of relativity equations, that universe must be expanded. And basically what Hubble observed was verification of this claim of Einstein. So what does this imply? Well, this implies that if you look all around from Earth to all directions, you will see that every galaxy, except a few very close galaxies like Andromeda or Triangulum, they are actually moving towards us. Gravity is pulling them towards us. We will eventually collide with Andromeda galaxy. But if we go a little bit away, the galaxies are moving away from us. Well, there are two ways you can explain this. You can think that Earth is at the center of the universe, or our galaxy is at the center of the universe, and everything is moving away from us. This is one way you can interpret it. And of course, not many people will like this interpretation because it implies that somehow our galaxy and our planet is in special place. The second way you can interpret it, this is that to think all the universe as a surface of a balloon. If you wish, we have a four-dimensional space, and the surface of this balloon is three-dimensional, and this balloon is being blown. Of course, it's hard to imagine three-dimensional balloon, so that's why let's imagine two-dimensional balloon. So we put points to this balloon, and we are blowing. Choose any point, no matter which point you choose. Suppose let me choose this point here. If you look from this point, which I assume represents a galaxy, as the balloon is expanding, as we blow to the balloon, no matter which point we look outside our point, we will see that they are moving away from the place we choose, or the place we are standing. And no matter which point you choose, take this one and look at other points, again, you will see that they are expanding. So this is what is happening. All galaxies are moving away from each other. It's nothing special about our galaxy. Every galaxy is moving away from every other galaxy. So this is what we think Hubble demonstrates. And this is what actually Einstein's equations predict. Our universe is expanding. Okay, this is an empirical discovery, and our equations tells that universe is expanding. What's the meaning of this? Well, since universe is expanding, in science, what we like is always to turn back the movie and think what was the state of the universe in the past. And if you slowly turn the movie backwards, of course, all the galaxies will come closer and closer and closer to each other. And eventually, they will meet each other at a single point, which means all the universe in the past was in a single point which expanded. And this expansion event of a single point is the Big Bang. It happened, you can make a careful calculations based on observation. This event happened before 30.7 billion years ago, which means that our universe began to exist before 30.7 million years ago. And this is the beginning of not only the matter, I will shortly tell you the story of how matter was created, but it's also the beginning of space and time. Okay, so far so good. So we arrived at the Big Bang Theory. Now we will expand a little bit details of the Big Bang Theory. But before it, I want to point out to some other experimental or observational fact. when you look at some distant object, you are actually seeing the past of that object. You are not seeing that object at the moment. What do I mean? Suppose we look at the sun in the morning. So you may be thinking that you are seeing the picture of the sun at that moment. What's happening at the sun at that moment? Well, it's not true. Why? Because light travels with finite velocity, 300,000 kilometers per second. It's a very big speed. Actually, that's the highest speed an object can move in the universe, but nevertheless, it's finite, which means for any distant object, it takes time for light to reach us. And when it reaches us, we see the picture of the moment that light left that object, which means, for example, we see the moment of sun, the picture of sun at which the light left it, which is actually like 8 minutes before. So we are seeing the 8 minutes before our moment, what was happening in the sun. If sun is destroyed, it will take like 8 minutes for us to learn this truth. In fact, also gravity moves with the speed of light, which means we'll not even feel it nor see it, what happened in the sun for 8 minutes. Of course, if we move further away, for example, we may look at our nearest star. It takes like around 4.5 years for the light to reach us from the nearest star, which means when we look at the nearest star, we are seeing around 5 years ago what was happening there. You can go and look at the further objects and you will see the past of that object. In fact, if you look so far away, you may be seeing what was happening before, say, 10 billion years ago. So basically, while Big Bang theory is partly a theoretical construct, which means we use our theories to understand what was happening in the past, we can also observe real time what is happening in the past, given it's visible from Earth. And I will explain what I mean by being visible. There is a limit how much past we can observe, but still it's so far away that we can see the earliest stars being formed. So it's not just a theory that stars are created later. They are not eternal or there was always stars. It's observation. Okay, so far, so good. So what does Big Bang theory tell us about how the universe and the objects inside it were created? As I said, everything began to exist before 30.7 billion years ago. There was an expansion, the so-called Big Bang, and the initial moment cannot be described by the laws of nature we know at the moment. They simply break down. So we don't really know what was happening at exact beginning, which actually opens up the possibility that it's not really an exact beginning. Perhaps our universe was part of some other multiverse and it simply shifted. So since laws of nature break at that point and we cannot observe at that point, it's open for speculations. However, after the initial moment, basically, we know what happens. Much clearly thanks to the laws of nature. We can explain what is happening after the first, what we call Planck epoch, which is actually this number you see here in the screen. So what happened? So initially the universe expanded. It was really, really hot, and as it's expanded, it's cooling down. At the initial moments, the most basic building blocks of the matter were created. Energy turned them into a mass and matter, and electrons were created, quarks were created. So all the matter you see around you are made up of atoms, and they are further made up of protons, neutrons, and electrons, and protons and neutrons are further made up of 3 quarks each, up and down quark, which means the most basic building blocks of the matter are electrons and quarks. And they were created in the first 1 millionth of a second. Once they were created, the universe was cooling down. The real reason why they cannot be created anymore in empty space is that the temperature falls down. As the temperature falls down, nuclear events stop and new events start. So eventually, in the first 1 second or 10 seconds, up to 10 seconds, the protons, neutrons, and quarks were formed. Every quark and proton and neutron which exist in the nature was created at that moment. Then the temperature cooled so much that no longer they could be created. The first 380,000 years after the Big Bang, the earliest, the state of the universe was what we call a plasma state. There are 4 states of matter. As you know, there is a solid matter, which you know, like the table and the chair. There is air, like the atmosphere, which you can now touch. There is liquids, like water. And there is the 4th state of matter, which we call plasma. In plasma state, electrons are free to move. They leave the atom and they freely move. So essentially, at the first 380,000 years after the Big Bang, electrons were freely moving, which means all the matter was organized in plasma. Still, actually, plasma is the most widespread state of matter. Stars are in the plasma state, but initially everything was plasma. So what happened then? Well, eventually temperature dropped below 10,000 degrees Celsius. At that point, electrons now could merge with the nucleus and the first atoms were formed. Initially, there were just 3 types of atoms, 3 most light and basic atoms. Hydrogen, which has a single proton and single electron, or they may have neutrons. Helium, 2 protons and 2 electrons. It was in a much lower number compared to the hydrogen, and a little bit lithium, 3 protons and 3 electrons. No other atom existed besides these 3 lightest atoms. So you may ask, well, where does the heavier elements are created? Like, where did the carbon, oxygen, gold, iron was formed? Well, they were formed in the stars. After approximately 200 to 300 million years after the Big Bang, the first stars started to form. They were formed thanks to the gravity, so everything which has a mass attracts each other. So we have a cloud of gases in the universe made up of hydrogen and helium. They are attracted by the gravity and they form huge clouds of gravity, which are bound by the gravity and they are forced to a tiny space at which nuclear reactions start and the first stars light up. Stars, we think them as a source of heat and light, which is true, but actually they are more also source of heavier atoms. They combine hydrogen and helium and form much bigger atoms, what we call nuclear synthesis, alchemy. If you wish, you can see it's a real alchemy. You take some form of a matter and you form another type of matter. You take hydrogen and helium, you form, for example, in the end, iron. So stars, they make all the elements up to iron. Everything which, you know, like oxygen, calcium, these are all carbon, these are all made inside the stars. Eventually, when the stars form iron, they cannot combine iron atoms to make heavier elements. That's the point at which stars die, via what we call supernova explosions. Everything below iron, that's why it's very cheap, actually. They are formed in the stars, and in every second they are being formed, so you can find all of them in space anywhere you want. But any atom which is heavier than iron is hard to come by, like uranium, plutonium, gold, silver, platinum. These are very expensive because they exist in small quantities, not just on Earth, everywhere in space, no matter you go, they are in small quantities. Why? Because they cannot be formed inside stars. they are formed when the stars die during these supernova explosions. And roughly you can think that it happens once in a century in each galaxy, and it takes around a minute. So they are made up in a very small, short time scales. That's why they are very rare in the universe. Anyway, but what is important for us is that all the matter we see around us is made up in the stars, thanks to stars, and that they are very important since because if the stars didn't exist, we wouldn't have carbon, oxygen, and therefore we wouldn't have chemical life, like the human life or in general life on Earth, would be absent. We require stars to make up the basic elements which make our body and every processes as we live on. We will return back to this at the end of the lecture, so that's why I'm pointing to this fact. Okay, so far so good. There's one more thing which I forgot to tell you, which is important in our story, is I said, actually I told it, but I didn't tell the importance. Around 380,000 years after the Big Bang, I said we switched from plasma to the gas state. Basically, electrons were captured by the atoms, which were hydrogen and helium atoms, as I said initially at the beginning stages of the universe. So we have just single three types of atoms, I say. So this point is important point because in the plasma state, light cannot travel freely, which means the first 380,000 years of the universe cannot be observed with our eyes. Basically, we cannot really use telescopes to see what was happening at that time. I said to you, if you look further away from Earth, we are also seeing the past state of that place. But for it, light should be able to move freely. But light was freed at 380,000 years after the Big Bang, which means the first 380,000 years time of the universe, which taken actually the astronomical scale is very small time. It's like less than a second, but this state cannot be observed with human eye directly. Which means there are two ways you can describe this state, either using theory or you can recreate the conditions on Earth, which was done actually in CERN. You can recreate the conditions, these high temperatures, and see what is really happening. Is these particles really being created, for example? Well, actually, the observations on Earth in laboratory, in which artificially we create the earliest states of the universe, actually confirm the theory. So even though we cannot directly observe, we can still talk about it. We can still say that it is experimentally verified because we can recreate the conditions on Earth. Anyway, and at this point, I say light was left to move freely. And actually, the primordial light which created the elements, was also left freely to move. Since elements were created everywhere, this light is everywhere. There is a light inside the universe which is everywhere. Of course, because the temperature cooled down, this light is not observable to eye. It has a very low energy. And actually, you can measure it, and it was discovered. It's called microwave background radiation because it is in the microwave regime. It has the same energy as the waves you create in your microwave oven, which is actually very low energy. Because you are cooking, you may think that it has a high energy. No, actually, it's very low energy. Microwaves don't have a big energy. Anyway, so before finishing the discussion of the Big Bang, the science part, I want to point out some evidence which supports the Big Bang. Already, I told you the initial evidence that is continued expansion of the universe. The only way you can explain this expansion is the Big Bang model. Of course, you can think, as I said, there was something before the Big Bang. You don't need to assume that that's the beginning of the universe. You may think some multiverse, you can speculate. But afterwards, what happened is really the only way you can explain is the model itself. Second, Big Bang theory, as I said, predicts that light was set free at 380,000 1,000 years after the Big Bang. This light should be in the microwave regime, and it should be observable from every side of the universe because it was present everywhere and it should be present everywhere. This was discovered and measured, and the measurements match the theoretically expected values, which is the second important evidence for the Big Bang. Lastly, I told you that initially there was just hydrogen, helium, and lithium. From here, you can say that still, since we are at the earliest stages of the universe, still more stars are being born than they are dying. Actually, it's like 4:1 around the ratio. So more stars are being created than they are dying. We are very young. So we should expect that majority of the chemical elements in the universe are made up of still the basic structures, hydrogen and helium. In fact, theory says that around 75% of matter should be hydrogen and 25% of the matter should be helium. And you can easily use spectroscopy. You can take the light, and light is the fingerprint of the elements it is passing from. So if you analyze the light, you can actually see what's the chemical composition of the universe. And the studies clearly match the predictions of the Big Bang model. So these three confirmations provide a strong evidence in favor of the Big Bang. So actually, the microwave background radiation was discovered in 1964, but by these two engineers, they were not aware actually that they created the most sensitive detector. So they were trying to create a communication device actually, and they were taking a static parasite signals from each side of the universe. So they were searching for the source, and they were thinking that there's something wrong with the device, but eventually they realized that it's not a mistake. There is a light coming from each direction of the universe. And basically, their discovery was later confirmed by measurements from the satellites, like which we sent to the space, and this light coming from each direction was basically analyzed and mapped out. It's a first picture of our universe. It's actually the baby picture of our universe. It shows the state of the universe at the moment when light was set free, 380,000 years after the Big Bang. Of course, this light, discovery of this light can only be explained by Big Bang model. Expansion of the universe could be explained by alternative models at that time, but this was the strongest argument in favor of Big Bang model, because there's no way in other models like steady state theory which can explain why the universe has this radiation. What's the source of this radiation? The source is Big Bang itself, and it provides clear-cut evidence that such an event really happened. And as I said, at the beginning, hydrogen and helium was mostly formed. We predict that the theory predicts that like 75% of the matter in the universe should be, again, by matter I mean observable matter, because there are some other forms of matter, but 75% of the observable matter should be made up of hydrogen, and 25% should be made up of helium, and the rest should be less than 1%. And exactly this prediction matches the observations. So these all together, they provide a very strong support to the Big Bang theory, which is now widely accepted model of how universe came to be. Okay. Before finishing the scientific part, actually we learned the basics of the Big Bang model. I want to point out to something interesting which is related again to what we are discussing. Well, universe is expanding. How is the speed of expansion of the universe changing? So initially you would think that expansion velocity should decrease. Why? Well, suppose I throw a ball into the space. It's kind of expansion, right? ball and the Earth are moving away from each other. It's like a big bang. But gravity eventually will catch the ball. Of course, ball is also exerting gravity to Earth. You may say ball is catching the Earth. They are the same. So they will again unite. The ball will fall down. Why? Due to gravity. So you expect same thing to happen. There was a big bang. Particles, mass particles are moving each direction. They form galaxies, but nevertheless, they are exerting gravity to each other. So you would expect that the expansion will slow down and eventually everything will turn back and collide at the center. Again, it is possible with several methods to measure how the velocity of the galaxies change, because since we can observe the past, we can also measure the velocity of objects in the past. And we can compare and try to predict what's the velocity, how the velocity is changing as we move away. Well, the result is surprising and has surprised scientists, especially when it was discovered. Now it's accepted by everyone. The expansion speed or velocity of the universe is getting faster and faster. So it's accelerating. It's like you throw the ball and ball is moving away from Earth, and its velocity is increasing and increasing, constantly increasing. It means there is something which is pushing away the galaxies. So that's what is increasing the velocity. So what's that thing which is pushing away the galaxies? Well, we don't really know. But we have a good and interesting term which we use to describe it. It's called dark energy. But basically, it's dark energy which is causing this expansion. We have some ideas what this dark energy may be. It's not that it's a complete mystery, we have no idea, but we don't really know specifically. We may be wrong. So we are not sure what really this dark energy is. But what do we know is that it is pushing away the galaxies, which means the expansion velocity of the universe is increasing, getting faster and faster. This started to happen, so this acceleration process began before 2.7 billion years ago. Before it was slowing down, now it's expanding. Okay, why did I tell you this fact? Well, actually, this dark energy can be used to explain what will happen at the end. So we know the past of the universe. Using the same method, basically we use the laws of nature to go back and see what will happen. Again, using laws of nature, you can fast forward to the future and predict what you will expect to happen in the universe. And basically, this brings us two possible scenarios. Since the expansion velocity is accelerating, the matter will not turn back. Most likely, never the matter will again meet with each other. That's the distant galaxies never will come back together. There will be no turn back. Everything will continue to expand. And there are basically two possibilities. If dark energy is not so strong, that's the force expanding the universe is not so strong, universe will continue to expand. It will continue to get bigger and bigger, but the acceleration will not be very radical, which means slowly the universe will slow down, all the stars will die eventually, and everything will end in what we call heat death. Universe will reach the maximum entropy, the stars will die, and what you will have is a huge collection of black holes, which probably they will also die eventually, disintegrate with Hawking radiation, and that will be the end of the universe. If dark energy is much stronger, it has a high velocity, it has a high value, much higher value than the first scenario, the expansion will become so fast that not only it will affect the galaxies, but it will start to push away the stars. It will start to push away the Earth and Sun, for example. Then it will start to push away even atoms. So everything will disintegrate into a smaller possible particle before it can reach the heat death. And this is called Big Rip scenario. Which one will happen? At the moment, we cannot really differentiate two theories because the values are so close to each other. We cannot really observationally differentiate which scenario will happen. We don't really know. We are not sure. But one thing, if the laws of nature doesn't change, or if we don't turn up to discover new laws, these two are the most likely possible scenarios about the end of the universe. Okay. So far what we discussed was the science of the Big Bang. So we got familiar with the Big Bang theory and the basic mechanics of how it works. Now we can think about what would be its implications for the debate of atheism and Islam, or in general theism. By theism, I mean the belief that there is a God, a single. We will assume that a single God exists. Actually, Big Bang, in my opinion, provides a good reason to believe that there is a single God, but as we will talk. So by theism, I will mean that there is a creator of the universe as described by Islam, Christianity, Judaism, and other monotheistic traditions. So basically, in my opinion, Big Bang provides support to the existence of such an entity by providing support to three traditional arguments for the existence of God. So we should be careful here. No scientific theory can prove or disprove the existence of God. It's beyond the limits of science. Science works with empirical data and make predictions again about the empirical data. So laws of nature describe how matter works, how physical entities work, and this is based on observation of the physical entities. So therefore, in itself, science cannot really talk about supernatural entities as God. It cannot make a description. It cannot really tell you how God is or how God operates in the universe directly. But it can, combined with some philosophical principles, it can be used to argue for the existence of God. So that's why no one should really see the Big Bang itself as proving or disproving the existence of God, but Big Bang combined with some reasonable assumptions can be used to argue for the existence of God. So what are these extra assumptions? As I said, actually, these are not the new assumptions. These are traditional arguments which are used to argue for the existence of God. So I believe three arguments, and I will provide a short summary for each of them. Argument from contingency, Kalam cosmological argument, and fine-tuning argument is tightly connected or is supported by the Big Bang theory.